All right. Good to see everybody here. Thanks for joining us once more. Again, we've been doing these live streams now for about 3 months, and we've created quite a collection. It's over on YouTube if you search for DevRev, and excited to have you guys join us there. Also excited to have audience members who are interested in the technology behind DevRev join us on our Discord server. So I think somebody's going to post that up here. So you can actually grab that link and hopefully join us, and we can have a nice dialogue over there. But today, for the next 25 minutes or so, we have the pleasure of having with me Devanshu. Devanshu, good to see you.
Hey, yeah, me too. It's a very surreal opportunity to sort of talk about the things you've done to a broader audience than just your teammate.
Absolutely. This is somewhat of a public show and tell, if you will. So I'm in Raleigh, North Carolina. I actually just took an overnight flight. So if anybody hears planes in the background, it's probably because I'm in the hotel right next to the airport for at least the next hour. And Devanshu, where are you?
I'm also in my hometown. I'm in Nagpur. It's interesting fact tidbit. There's a stone in Nagpur which marks the center of India. So literal center of India is there is the stone kept in Nagpur. So if you want to know.
And you're how close to the stone are you right now?
4 or 5 kilometers.
Okay, I mean that's still pretty far. Okay, yeah. But you're not exactly there, but you're close enough. Okay, so I mean, I guess we're in the center of the search conversation, you could say, because last week we talked about search as well. And for today, what we wanted to do is really talk about a technology that a lot of people might have heard of. It's OpenSearch. It's available. It's an Amazon offering. It's an open source offering, and I think that it's a technology that obviously we've built quite a bit of our pipeline around. And before we got into OpenSearch, what we wanted to do is just kind of talk about what it takes to actually build a really great search solution. And that includes technologies like OpenSearch, but it includes many other steps as well. Pratik took us through some things. Where do you want to start today as we talk about OpenSearch and what it takes to scale our results?
Right. So we'll talk about a few things, but first, which sort of is magical in some sense, is semantic search. We'll see what semantic search is, one small example first, and then we'll talk about more how OpenSearch really helps us enable semantic search at a scale that is huge and something we had not experienced before, and now we are sort of planning for it.
Awesome. So let's have a look at a sample example, and then I think people will get a flavor for what semantic search is if they don't already know, and then we can proceed with talking about the details.
Awesome. So this is our DevRev instance. I'm doing a command K, and this is a search agent. I should have done a reset before, but okay. Now, so good evening. Now we are going to ask, are there any issues? Issues is a work item that we have. It's a native object. Are there any issues related to?
And of course, while you're typing that, I'll just say that this is just a fictitious organization that Devanshu's created here. So while you're typing, so I mean, obviously we're not often asking about fruits, but you know, in this particular case, that's the subject matter. And what do we see?
So I did this. Now it's the agent has started doing its thing. It's trying to search things, and it should end here, right? Good, sweet. So it found 2 sources. Right? There's one which is purchase inventory for snack bar, and then there's a setup fruit bar on the 3rd floor.
Okay.
And then it gives like a good summary of both of them. Now, the key point to note here is purchase inventory for snack bar. If I open this issue, I close this for a bit. Purchase inventory for snack bar, we need some apples, oranges, blah, 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 blah. So nowhere is the word fruit mentioned, so to speak.
Yeah.
But still it came up.
Yeah, and what you're showing here is the fact that this is not just a lexical search. This is not a keyword search. This is really understanding that fruits are examples of fruits include apples, mangoes, pineapples, and hence there's a strong correlation.
Correct. So that is what semantic search is for us, and this helps enrich pretty much anything that you do in DevRev, any sort of agent interaction, any agent interaction and any search queries, any recommendation items, any deflections, everything is enriched using semantic search.
Yeah, and really that's been the big unlock even for enterprises over the last 5 years, or let's say maybe last 2 years, perhaps mainly for most companies, is the fact that conversational search is driven by these better understanding these semantic relationships that are now better understood. So semantic search is coming along in a big way, and probably many of us, or maybe audience members that are watching this, they've probably already experienced this, and it's a big shift, right? It's obviously a huge leap forward.
Right. To bring to your point, it's so recent as to any cool company that you've heard of, Pinecone Quadrant, any of the vector database solutions out there, everything started after 2021. So it's really picking up as we speak.
So let's actually start the conversation there. We don't have to spend a lot of time on this, but obviously you and I have both been here at DevRef since 2021, and we actually distinctly remember working on vector databases for semantic index. And that was back when, yes, there were a few smaller shops working on vector databases, and we can talk about a couple of those, but it was nothing like what we have now. I mean, the technologies weren't quite there, and for what we were trying to do, which was be an at-scale multi-tenant store that was going to be available to people, even free to try before you actually purchased and upgraded and things like that. Obviously, there was nothing really on the market that matched those needs. Can you add a little bit about that?
Yeah, sure. So there was this vector database that a bunch of my friends, colleagues built. It was called Honeycomb.
Yeah.
Let's see how it worked.
And Honeycomb was a proprietary vector database that we based our technology on, our semantic search on, in the early days. And this is prior to, bringing some of the goodness over to OpenSearch. But yeah, let's talk about what we were doing at the time and what were the foundational pieces.
Yeah, the sort of cool part is we also, I think 5 months back, we got the patent granted for Honeycomb.
Okay.
Yeah, that's cool. Now we have, this is like the structure of Honeycomb in like a very zoomed out view.
Yep.
We have the Honeycomb service here, and any user is making a query to do a semantic search.
Yep.
It says k nearest vectors. So the small nuance there is, whenever I type an English sentence, the first thing that happens is you take that English sentence, you convert it into an embedding, and that embedding goes to a vector database. So the embedding comes in. Now there's 3 components to Honeycomb. One is S3, then there's Postgres, and then there's Redis. S3 is the source of truth, so to speak. All the vectors are stored in an indexed format in S3. The index that we primarily used was called IVF. So imagine there's all the vectors are clubbed into different clusters. Those clusters are clubbed into different clusters. So these clustered vectors are then stored into S3. Whenever search request comes in, what first happens is it finds whatever key the thing has to be looked up in. So if it's an issue or a ticket or anything, and then it first hits Redis. Because S3 is like an over the network call, it takes time. So we first hit Redis to get like quick answers to all the vectors. And if there's like cache misses and stuff, we go to S3. Now the cool part is, if we keep this live, like indexing happens at like breakneck speeds at times. When like huge airdrops come in, there's like at times we found 50 million objects being indexed in like a matter of days. And in that case, if we make a write call to S3 for every vector that's indexed, it basically will burn the bank and also will cost like a lot of time. So what happens is Postgres is the running storage. So things keep getting inserted into Postgres in like a ordered format. And whenever a search request comes in, the data from Postgres is amended using the data from S3, and then it's returned back to the user. And every so often, Postgres is flushed into S3. So that really enables real-timeness while keeping costs and latency in check.
Yeah. And I think this was a pretty good project for us to get going with back in 2021, because we started to get a lot of firsthand experience with really understanding the entire pipeline for having good embeddings, understanding business ontology, understanding how to map, the actual process of creating embeddings to a real pipeline where we are measuring latencies, both in terms of ingest and then, of course, retrieval itself. And so it taught us a great many things, but all the while, if you recall, we were paying attention to what was going on and trying to figure out who out there would be able to do things that would allow us to actually, hitch our wagon, so to speak. And a couple of the things that we were always hoping to do better at, in those early days, like any system, retrieval system or data storage system, it has to do with how you deal with predicates, namely filters and joins. Do you want to tell me a little bit about the journey we took to actually get better with handling filters at scale?
So let's do demos again.
Yeah. Okay.
Let's go. So we'll go to search agent again. I'll start a new conversation to some
Okay.
people who are not cheating. Now we'll ask what are there any issues owned by me that are about getting fruits?
And while Devanshu, you're typing that, I mean, when you say that are getting fruits, when you're saying by me, typically speaking, now if somebody out there is a SQL expert, they know, that those are going to be translated into what we call predicates or things that create a level of selectivity where you start to filter the result set to make sure that maybe you're looking at issues, but that you're looking at issues by Devanshu or whatever the case might be. So we translate these things into what we call filter factors. And the same thing is happening here when you're talking about a vector database. So go ahead and run this thing and let's see what happens. And so I think it's important for us to understand that the better the system, at least at scale, it has to be able to do a really good job of translating those predicates, those filters, into sort of real-time selectivity predicates that can run quickly. And so here, I guess the response was pretty quick. What do you think of the response?
Yeah. So if you remember, the first search that we made was about issues related to fruits, and two came up, but only one of them was assigned to me. And when I asked about this specific question, the new ones being owned by me, it only gave back one issue. And this is critically important, especially so when you have millions, hundreds and thousands of issues, because you want to, when you're inside the database, put in the predicate in it, not something that you think of after the fact. The database has to be optimized for doing these predicate evaluations. And here it tells me, okay, we want 30 apples, 5 pineapples, 30 mangoes, 15 kiwis, and so on. So yeah, this is how filtering sort of brings in life to any sort of search, more so for semantic search, because semantic search and filtering were never really thought of married together until very recently. Any vector database engine out there only stored vectors, and you could just do KNNs. So yeah, that's one of the very important parts.
Yeah, I think this concept of pushing down predicates has been around in certainly in databases for a very long time. And by the way, guys and gals, whoever is joining us here, if you want to continue this conversation, or if we talk about subject matter, details that perhaps you want to double click into, you're welcome to join us on the Discord server and ask us directly, and we'll be happy to answer those questions. But coming back to Devanshu, I think pushing down predicates and making sure that these are actually being processed at the time of actually bringing result sets back for re-ranking is going to be way more efficient than actually bringing in a superset of results and then trying to figure it out at the re-ranking step. So if you actually have a search pipeline, a retrieval pipeline, if you don't support predicates or filters natively, what you end up doing is you end up actually going and overshooting, getting a bunch of results, assuming that certainly many of them are not going to pass the filter, but you don't know how many. And so you have to overshoot by some factor. And you could say, okay, if I want to choose between the top 5 to 10 responses, what I'll do is I'll go and get 50. Or if you want to pick between the top 10, 20 responses, you might have to go out there and get 200 or 500 results, only to then create a subset which matches your predicate. And you could get unlucky there as well, or you might realize that you went and got way too many results and just increased your compute for no reason. So these types of guesswork steps you want to avoid if you can, and that's where the predicate pushdown really helps out. So basically, if the filters are natively expressed in the vector database, you're going to get better results. And so that was something I guess we waited on here, and OpenSearch, I guess, provides that.
Yeah, it does. It does. In there too, it was like a very joining journey, because OpenSearch was also slowly bringing in push down predicates than doing post facto analysis. So we have like this 100, 200 email chains where we are sort of collaborating as to how to get that stuff of that sort. Yeah,
yeah, I'm sure. I guess we won't be putting those on Discord, but if you guys want to know about what that journey looked like, certainly happy to talk about it. But I think if you're going to talk about filters, there's sort of the advanced version of filters, which is joins, which are effectively filters, like multiple filters that have to be processed together. Do you want to talk about joins as well?
Yeah, let's go.
Okay.
So one very common thing that I believe most of us would be going through, this being one, is meetings. And meetings can, in some sense, run very longer, in hours, 10 hours, whatever. Yeah. So when we want to ask questions for meetings, it's in some sense the common proverb, right? Finding the needle in a haystack.
Yeah.
So let's see how meeting answering really works out. Let's go to my meetings.
Yeah.
Meeting is completed. So let me remove this. Yeah. So there's a meeting called backend search scaling and feature planning. And
Okay.
then I have attached a transcript here. Let me open this transcript up. Give me a second. I will open this up here. Right. So there's like a bunch of like a very generic transcript. There's the person speaking it and what they spoke and at what timestamp. And it goes, this is still not that huge, but big enough for you to not immediately find out what is what and parse things in like a sensible way. So let's go and ask a question about, where is my tab? Yeah, let's go and ask a question about this.
Yeah, and while you're asking the question, what I'll say is, and I'm not sure how pervasive this is across this audience, but certainly we've seen a lot of organizations where they've set up meetings and also set up meeting transcriptions. And those meeting transcriptions, thanks to workflows and automations, they will automatically transcribe meetings and also associate voices with individuals who are attending the meetings and actually bring all that information into the meeting object, and those attachments can be processed further. And of course, you can access some of that information the way Devanshu is accessing it. You can do a great many things with that information, but among those is being able to retrieve information about the meeting or what was discussed in the meeting conversationally.
So I typed I typed in here. So this is a very natural occurrence that would come up in like actual execution. So here I ask you, what did Rahul propose as a mitigation plan for like downtimes? And this would actually come up when like I'm coding it up and I'm like immediately like, oh, what happens when there's a downtime? And this is like a quick way to find out what happened in the meeting.
That's
and then
right.
Here, if you look at it, it like very perfectly like bulleted form. It tells us, okay, Rahul said that we could do it simultaneously, we could do it sync processes. The important part here is the sources mentions the search scaling.txt. Here I've manually uploaded it, but we have various sort of snap-ins to do auto injection with whatever transcribing.
Absolutely. Yeah, as we mentioned.
Yeah. So search scaling txt. Now the important part here is this is still a medium length transcript. If the transcript were 10x more, this feature would still work. And the good part why it works is we do a chunking of the transcript. We chunk it into multiple parts in a form that still preserves the merit of the transcript. And when we are doing a search query, we make a join query on all the chunks with the meeting object and then retrieve for you the meeting object while leveraging the individual chunks during the search. And the cool part is, if you, while we sort of pride ourselves in like good chunking strategies, but if you want to try and experiment on your own, you could write your own chunking strategy. So everything is workflow driven. So here there's a workflow that we've written for chunking meeting transcripts. So whenever meeting is created, for every transcript, we do like our custom chunking here, which you can obviously choose to do in whichever way you want to.
Yeah, and I'll just add, I mean, as much as we are, going to be transparent in these conversations, obviously there's certain proprietary algorithms that we use, particularly in search and retrieval. There's just a lot of very specific, techniques that people learn, sometimes through extensive testing, trial and error, empirical validation. And obviously we're not going to overshare some of that information. But here we're trying to show that anybody can do sort of a sample chunking and start to see for themselves some of these results.
Right. Yeah. That's how joins play into things. I'll show you like the general form if you want to.
Yeah, please.
Okay. So this is how like any general chunking sort of works. So there's the meeting. Then you can do a transformation of the transcript in whatever form you want to, initial transformation, right? And then you split it into different chunks. The splitting is sort of the critical sort of secret sauce, if you will. You have to split it in a way that's still coherent and everything still gels well. And once you split it, there's like another transformation if you want to, and then all these transformed chunks get indexed separately. And these separately indexed chunks when being searched on are joined, these things are joined with the parent meeting object to retrieve the results for you.
Yep. Now, of course, so far you've shown us a couple of sample questions being answered. Thank you very much. You talked about issues, and you very specifically said issues are sort of this way of conveying work that's being done. Then you talked about meetings. I think it's pretty self-explanatory what meetings are. But both of these are sort of these native objects. But what happens is a lot of times when we're doing search, and especially when we're talking about vector databases and OpenSearch and the needs that we have, you have to support the long tail of terminology that exists in businesses. And the way we do that natively is by creating custom objects and custom attributes. And so one of the challenges that we have to face that I think offered us an opportunity to be quite innovative, and it was a central part of our sort of working with OpenSearch, was being able to support custom objects, arbitrary custom objects that we have not seen before. So tell me a little bit about that journey.
Right. So one, at least from what I've explored and experienced, one important part with any database out there, MongoDB, OpenSearch, anything, is the index is very memory intensive and very compute intensive. It takes resources. So if you want to do quick searching on many things, it is very expensive. So in here, as Ahmed mentioned, custom objects are something very custom to your workspace, to your org. And if we have like 1 million customers and every of them have like 100 different fields and custom objects, 100 million fields need to be quickly and efficiently searched over. So we come into how that works in a bit. And first, let's see an example in action. So there's this deployment object that I've created here. It's a very simple plain object. The idea of the deployment object is to show how deployments are being rolled out. Here I'll ask one thing: are there any deployments?
I mean, it's just a technology concept that probably most DevOps, SRE, cloud engineering folks are familiar with, which is the idea that a microservice needs to be rolled out so that it can serve requests. So in that case, we call that a deployment. And here what you're doing is just to kind of demonstrate custom objects. You've created an object that represents that. And it could be a case where you want to have in your system of record a log of all the deployments that are happening and when they're happening and so on and so forth. And that could help you. And of course, a lot of this information not being generated by humans, it's actually generated by systems that you use. Perhaps you're using Argo CD or you're using some other CI/CD technology, and that information supports webhooks, and those webhooks are actually creating these deployment entries as and when they're needed, and you can annotate them however you choose. And this is how a lot of businesses are starting to automate many of their back-end processes, their back office tasks. And so this is such an example where you've created this custom object and you're trying to convey that. Can we actually look at one of these records as we read this response?
Yes.
Okay. So you're going to click on one of these? Okay.
Yes, I did it. It's opened behind. Let's just first see that this replied with a deployment that's new OpenSearch based semantic search. And then we'll look at that deployment. So this is that deployment that it replied with. The question I had asked was, are there any deployments running for a duration greater than 15 days? Now, what that means is like, why would I want to ask that? So in here, the way I've defined the duration field is many a times deployments happen in a staggered form. So if like a new feature is coming in, you want to slowly like give it soak time, get it deployed. So whenever you want to see like, okay, are there any big features coming in, something that's being deployed for over 15 days, it's like a very sort of curiosity driven query that you may want to fire.
Yeah.
So here there's a deployment that's supposed to run for 30 days. And this is the new OpenSearch based semantic search. And so this is where.
And this is sort of I guess our fictitious definition of a deployment, meaning to say it's not about how long it takes to roll out the service, but in this particular case, you're talking about how long we want to actually start the process of rolling out a specific feature, let's suppose. It's possible that you're not only rolling out the service across regions, but then you're also enabling the feature, and then you're letting it sort of bake in one place, and then you're letting it bake with another cohort and then another cohort. And ultimately, it could be a full month between the first set of organizations that have a feature and the last set of. And to be honest, like there's probably people listening to this where there's many months that go between the first company that might be using feature A and the last, right, when it's available generally. So this is quite common, limited availability followed by general availability. But go on.
Yeah, so that was sort of the crux of it that you summarized quite well. This is how custom objects sort of played into how we do semantic search and how we do search in general. So this field, not just the field, the object in itself, but even the field is very custom to this org that I created. So when I'm doing a search in an agent, the agent has to first figure out, okay, there's a thing called custom objects, which could be plenty. From those custom objects, it has to figure out which custom object to search over. Once that's done, it has to then figure out which field to filter over. So that's the agent thinking brain part of it. Post that, in OpenSearch, there's like strict limits. So for giving you one like publicly available information, OpenSearch has a field limit of 1,000 fields for an index. So in some sense, you only have 1,000 fields to play with. Yep. In that constraint, how do you ensure that you support virtually infinite fields to be filtered over, to be searched over, is the sort of cool part that helps. Comes in
and I know that there's some proprietary projection mappings and whatnot in that space. And of course, we've played around with that actual static number as well. So I don't know how much of that you're going to share here. But what I will say is that if a person's maybe hearing that and saying 1,000, that's plenty. Keep in mind, it might be enough for one organization. But remember, this is a system that's supporting potentially hundreds of thousands of organizations. And each of those organizations over time will actually start to generate hundreds, if not thousands, of custom objects and custom attributes within those objects. And so the numbers start to scale out pretty rapidly. And so you need to come up with a way of actually spacing, swim laning information, and of course, testing the limits to make sure that not only does it work functionally, but it actually performs. But go on.
Yeah, I think that was sort of the crux of it. I wouldn't want to delve into details because I don't know where I'll slip up. But yeah, that's kind of...
Okay, so we'll probably be able to share a little more about how we played with that 1,000 limit. The short answer is we did a lot of cool things. And if you guys want to know more, join us on the Discord server and we can talk about it. But Devanshu, where do we want to go from here? Because we've talked about just the fact that we kind of dabbled with our vector search. We started building a relationship with the OpenSearch party. We got serious about filters, joins. We talked about, of course, customization and how it throws a monkey wrench, but we had to get past that as well. Let's talk a little bit about the number one thing that we needed to make this thing actually scale, which was the word that we've heard a lot when it comes to large language models and actually shrinking them, which is quantization.
Right. Okay, so let's do a segue into more things than just quantization. So when we are benchmarking things, let me do OpenSearch again.
Yep.
So when we're benchmarking a different vector database, different things, this is where we sort of did all the visualizations. We fixed what sort of hyperparameters to tune. So some hyperparameters are, so OpenSearch has number shards, right? So OpenSearch has shards, then how many shards to pick that impacts search speed, that impacts uploading speed, indexing speed. So in there, one attribute that we played with was quantization. So the way quantization works is whenever you storing a vector in a vector database, every element of the vector, let's say it's like a 768 dimensional vector, every element of those 768 dimensions is a floating point. Those floating points usually take 32 bits of information on the storage engine or on the RAM. And when so let me come here for a bit. So what the index that we're using is called HNSW. This is like a photo that I borrowed from Pinecone. This is how HNSW works. It's a graph. It's like a multi-layered graph, and every node of the graph is a vector. So whenever you want to do a search, you have to traverse this graph. And to traverse this graph, you have to bring the graph in memory. And imagine doing that for millions, hundreds of millions of vectors. At this point also, we have more than 100 million vectors in individual regions that we operate in. So bringing in so much into memory is extremely cost prohibitive. So the way this works out is quantization. So one cool form quantization is done in OpenSearch is called binary quantization, in which all the 768 numbers, instead of being 32-bit floats, get converted down to 1 bit. So it's basically 10101010 for 768 times. And these 32x compressed graphs are what are brought up into memory and then searched over So imagine it's not taken exactly 32x decrease in memory, but like a very high magnitude of decrease. And then there's cool things that are done to sort of oversample to ensure that the recall does not take a hit. So quantization is sort of that final piece. Even if we have everything right, we solve for custom fields, we solve for filtering, we ensure custom fields can go unbounded to ensure that it's within our budgets, to ensure that it operates at a thing that we can offer it to not just paying users. We can offer it to people for free. We can offer it to people to try. We can offer it to people with 3 credits. We wanted to ensure that we can do a quantized approach to keep our costs in check, and that's where quantization comes in.
And most importantly, that it actually scales. Is one thing to actually say, you know what, it's there, the index is available and it's supported, and we were able to create it. But it's an entirely other thing to say, you know what, it's so, memory intensive that it just doesn't scale, right? Or it scales poorly. So I think
yes,
the quantization has been huge. I mean, obviously, quantization is having a moment for the last 2.5 years or so, thanks to the same type of technologies being applied on the foundational models and many other models that are out there. And so obviously, we're learning from all the new technologies that are getting out there, and it's making its way into many different systems as well. So great to hear that. We're kind of past the 30-minute mark. That's typically where we like to land, Devanshu. So we're gonna have to have you back for more topics, and of course, we're gonna have to have people join us on Discord to continue this conversation. And obviously, we can also see messages and comments on YouTube, and maybe we'll respond there as well. Is there anything else? Like, what's next? What's your next chase before we wrap this up?
Next chase is to sort of take that scale and sort of consume it in like a very elegant sense. So we are trying to onboard customers, enable customers that have not just hundreds of thousands, but tens of millions of work items and things of that sort, right? Yeah. So when such huge airdrops come into our system, we should be able to gracefully index it quickly enough so that it's that immediate wow factor. You click the button, it comes in, you can start searching, and it just works. So therein, I'll show like a loaded graph here, but therein, this is just to drive the point that we're sort of very actively working on trying to optimize these things. We're trying to ensure that the indexing time, the time that an object enters DevRef system to the time that you start searching it, is basically zero, maybe imperceivable. And once that's done, it just harmonizes and it's magic.
So near real time, you're shooting for near real time ingestion.
Yes.
Okay, so I'm gonna let you get back to work. Thanks for spending the past half hour with us, and to the audience, thank you again for joining us. We do this so that people can start to understand the details of the work, but also appreciate the people behind the work. And so, Devanshu, you are one of those important people behind the work, and I appreciate your time.
Thank you.
Absolutely, and folks, we appreciate your time as well. Thanks again, and we'll see you again next week. Take care. Bye.
Take care. Thank you.
See you later.